In this video, we will talk about two different concepts on how to generalize the definition of a basis for a finite dimensional vector space to an infinite dimensional vector space. Hi, my name is Frank and welcome on my channel. We start by recalling the definition of a basis for a finite dimensional vector space. So let V be a finite dimensional vector space. We then call this set B, which contains vectors b0 up to bn. We call this a basis if B is linear independent, meaning if we have a linear combination of vectors B which is equal to 0, then all the coefficients alpha I, they already have to be 0. And second, it must span the whole base V, meaning that for every vector V in the vector space, there must exist a sequence of scalars such that we can find a linear combination of this vectors B, which is equal to our vector V. The existence of such a basis for a finite dimensional vector space can easily be proven. The question is, can this concept somehow be generalized to an infinite dimensional vector space? Is this possible? Did we run into some borders here, or do we have to extend it in a certain way? We start with the definition of a Hamel basis. The Hamel basis is, I guess, the straightforward extension of the definition for a basis in a finite dimensional vector space to an infinite dimensional vector space. So let V be a K vector space. In this case, we allow infinite dimensional vector spaces. We then call the set B a Hamel basis if it is, of course, linear independent, meaning that for all finite subsets, so this is important, so for all finite subsets must be linear independent, meaning, well, you can see a definition here. Furthermore, it must span the whole base V, meaning that for every V in our vector space, there exists a finite set of vectors in our set B such that we can form this linear combination here. So it's in red I marked the big difference to the definition of a finite dimensional basis. You can see here we all need finite subsets here. And this is a fine definition, and we can ask ourselves, well, does such a set exist at all? And if it exists, how does it look like? Can we somehow write it down? Before we come to the question whether such a Hamel basis can be constructed or not, let's deal with the existence first. Of course, we want that every vector space has a Hamel basis. So maybe we can prove this. We start with a very naive approach. We assume that V is not trivial. Well, because if it's trivial, there's nothing to prove. So if V is not trivial, we can find a set S1 which contains only one vector. If S1 already spans our vector space, well, this is a basis and we are done, there's nothing to prove. In fact, for a finite dimensional vector space, every basis is of course a Hamel basis, and the other way around, there's no way they are the same in this case. However, if S1 is not a basis of our vector space, well, then we can find a vector V which does not lie in the span of S1. Well, and then we append this vector to our set S1 and call this S2. By construction, this is now a larger linearly independent set. And again, either this is a basis or we can repeat this process. Well, if V is finite dimensional, this process will stop at one point and will give us a basis. If V is infinite dimensional, well, this process will go on forever, and it is clear that every SI will not be a basis and therefore will not be a Hamel basis at all, because every SI is a finite set. But we are smart, we just define the set S to be the union of all SI. This, of course, is, if V is infinite dimensional vector space, this is a linear independent set by construction, and it is infinite. So, in fact, it is countable. The question is this a basis? Well, I don't know, and we will answer this question later. Our naive approach, however, will not give a proof. This is not a proof at all because, well, there's nothing stated here. We need something stronger. M is something stronger, I mean something really strong. We need Zorn's lemma. Zorn's lemma is equivalent to the axiom of choice, so this is a very deep lemma in fact. What does it say? P should be here a partially ordered set, meaning that our operation, our comparison operator, less or equal, should be transitive, reflexive, and antisymmetric. Then we can define something which is called a chain. A chain is called a set T where this condition holds. So for all x and y in our set T, we know that either x is less or equal than y or y is less or equal than x. So the definition of a chain is straightforward. This is kind of a ordered, a chained set kind of. In addition, we assume that for every chain in our set P there exists an upper bound S. S does not have to lie in our set T, but it should be in the set P, of course, such that it is an upper bound. So upper bound meaning that T is less or equal than S for all T in P. If this assumption holds for all chains, then Zorn's lemma say, okay, there must be a maximal element in our set P, meaning that this maximal element is called M, meaning this M is less, that for all element x in P, this condition holds, meaning if M, our maximum element, is less or equal than x, well, then M is already x, or in the other way, x is already M. So we have a upper bound, a maximum element for all elements in P for our operator less or equal here. So how can this be helpful to prove the existence of a Hamel basis? Well, let's take a look at the proof. Of course, every vector space has a Hamel basis. Otherwise, this would be a very weird definition of a basis. How can we prove this? So P should be the subset of all linearly independent subsets of V. So it should lie somewhere in the power set of our vector space V. And we assume that Si is a chain, meaning that S1 is contained in S2, is contained in S3, and so on. This is a chain. Then we know that the set we have already defined, so the unions of all Si, is by construction linearly independent set, meaning that the union S lies in our set P. And by construction, every Si is contained in S. So it should be not an is element, but a subset. This is a small mistake, I'm sorry. But therefore, S is an upper bound for the given chain with respect to the is contained in operator. And since our chain was arbitrarily chosen, Zorn's lemma now states there exists a maximum element, let's call it B, which is contained in our set P. This means B is a linearly independent set, such that, well, every linear set in P is contained in our set B. We still have to prove that our set B actually spans the whole vector space. To do so, we assume that there exists a vector V which does not lie in the span of B. And we are given a finite but arbitrarily collection of vectors B1 up to Bn lying in the space in the set B. Now, we choose scalars alpha 1 up to alpha n plus 1, such that alpha 1 times B1 plus alpha 2 B2 and so on up to alpha n Bn minus alpha n plus 1 times V equals 0. We now have two possibilities. The first possibility is, well, alpha n plus 1 is not 0. If alpha n plus 1 is not 0, we could just divide this equation here by alpha n plus 1 and end up that we can express V as a linear combination, as a finite linear combination of our vectors B1 up to Bn. However, this is a contradiction to our assumption that V does not lie in the span of B. Well, then it must be the second possibility. So alpha n plus 1 must be 0. What happens in the case if alpha n plus 1 is 0? If alpha n plus 1 is 0,
well, then also alpha 1 up to alpha n must be 0 because, well, B is a linear independent set, and therefore the finite collection B1 up to Bn is linear independent, and therefore alpha 1 up to alpha n must be 0. However, this would mean that B united with our set V, our vector V, must be a linear independent set, because we have just proven linear independency under the assumption that alpha n plus 1 is 0. However, this is now a contradiction to the maximality of B. So, concluding, we have checked all possibilities, we have led all possibilities to contradiction, therefore such a V does not exist. And therefore V spans the whole vector space, and this now finishes the proof that every vector space has a Hamel basis.
Since we have used the axiom of choice in the form of Zorn's lemma, the set B or the Hamel basis cannot be explicitly constructed, and this is a major drawback since this is of course not useful for practical applications. A weird example, for instance, is the set R, so the set of real numbers. Of course, this can be constructed as a vector space over the field Q, and therefore exists a linearly independent set B containing real numbers, such that every real number can be expressed as a linear combination of vectors B, such that the coefficients Qi are rational numbers. And well, you can ask yourself a question, how does this set B look like? Well, nobody knows. And the second question is the set B countable or uncountable? Well, good question. Or another example, before we have to make use of a so-called Banach space. So a Banach space, which we call X, is just a complete normed space over the real numbers or the complex numbers usually. Complete means, of course, every Cauchy sequence converges in our space X, and normed means that we have a norm. And the convergence of the Cauchy sequence is, of course, with respect to the norm here. So nothing spectacular here. Then you can show, this is a very strong actual result, that every Banach space of an infinite dimensional does not have a countable Hamel basis. So in other words, a Hamel basis of a Banach space is uncountable. And the proof uses the so-called bare category theorem. It's a very useful result when it comes to deal with infinite dimensional spaces. And furthermore, this theorem shows that our naive approach by appending vectors to the set S and then building a union kind of will in general not give us a Hamel basis at all, because by our naive approach only countable sets have been created. But as you can see here, well, the Hamel basis is uncountable. So furthermore, we show that in general it is impossible to construct a Hamel basis as it is uncountable. And constructing uncountable sets or giving a plan how to construct the vectors containing an uncountable Hamel basis is hard, put it that way. I don't know if it's even possible. If you know whether it's possible or not to construct an uncountable Hamel basis, I would really appreciate it if you post it in the comments, because I don't know any example. Okay, so the question is there a different way to define the basis which is more useful when it comes to practical applications? Let's go back to the finite dimensional case for a second. We have the definition of a basis here, and we can ask ourselves, well, if it's possible to do this or to extend this for an infinite dimensional vector space, well, such we only place this n by infinity. Is this possible? So just replace this n by infinity. You can see definition here. Before we come to some definitions, we have to ask ourselves, well, how do we interpret this here? How is this understood? And to understood this infinite sum here, we need to equip V with a norm, or at least a topology, because now we can say, okay, V is this infinite sum here if the limit of this linear combination, of this finite linear combination, if this converges against our vector V. So now we know how to understand this infinite sum here. And well, let's just put it in a definition. So we assume that X is a Banach space, so X has a norm here. Then we say a Schauder basis is a sequence B0, B1, B2, and so on, such that for all elements in our vector space there exists a unique, and I want to point out this uniqueness here, if there exists a unique sequence of scalars such that this infinite sum here on the right is our vector V. So this is a fine definition, and obviously a Schauder basis is always countable because it's just a sequence and you can just count them. So this is called a Schauder basis. For instance, does such a Schauder basis exist? And well, they do exist, of course. Some famous examples here. This is the space, so small LP is the space of all sequences here in our space and here in the space R, such that the coefficients of our sequence, well, they satisfy a certain property. You can see it here. You can define a norm on the space, which you can see here. And this now forms a Banach space. Only, but take care, this is only for p greater or equal than 1. For this space, we can define a Schauder basis just by picking the unit vectors. So the unit vectors E1 has a 1 in the first component of the sequence and otherwise 0. E2 in the second component, otherwise 0, and so on. Then you can show that this is a Schauder basis. Or if you're more familiar with function spaces, the space big LP, of course for p less or equal, bigger or equal than 1, of course, also admits a Schauder basis, this so-called Haar system. And it was an open question whether the space of continuous function also admits a Schauder basis, and this is true, and this is called the Faber-Schauder basis. You can Google them and take a look at them if you're interested in such Schauder basis. And number 3, every orthonormal basis in a so-called separable Hilbert space is a Schauder basis. We will talk in a second about separability. And a small remark, the Haar system and the Faber-Schauder system, they can explicitly be constructed. There's a formula, put it in, and out comes your Schauder basis. Of course, you will never be able to construct all of them because there are infinite dimensional many, but in theory, it is possible since this is a countable set. Okay, I said we need a definition of separability. This is important because we need this for the existence of a Schauder basis and so on. And space is called separable if there exists a dense countable subset. So there's the definition. You need this a lot in function analysis. This is a very useful property and will give you a lot of stuff you will need. And then you can show very easily that every Banach space equipped with a Schauder basis has the separability property. This is very easy. Just take the span of all elements of the Schauder basis. Well, and this is of course is a countable set, and by construction this is dense. There you go. The inverse, however, is not true, and this was a long open question, also asked by Schauder. And the counterexample was given by P-N-Flow. Here you can see it in the 1970s. Not every separable Banach space has a Schauder basis. They work with the so-called approximity property. I don't go into details here. If you're interested, you will find, just ask Google, they will happily tell you where to find this proof. It's not that easy counterexample as you can imagine, but if you're interested, just take a look. Don't be afraid. But what you can show is that every infinite dimensional Banach space, well, it does not have a Schauder basis, but it has an infinite dimensional subspaces that has a Schauder basis. This is called the theorem of Mazur. And well, let's talk a little bit about the differences of a Schauder basis and a Hamel basis. Of course, the Schauder basis is much more useful when it comes to applications because you can explicitly write it down in most cases and you can work with them. You can use some approximation properties. You can simply work with them. Because if you have a Hamel basis, this is not possible because Hamel basis usually cannot be constructed. And furthermore, there's a big difference. In infinite dimensional Banach spaces, a Schauder basis can never be a Hamel basis. So these are completely different concepts. Obviously, you do this by cardinality. I've showed you, we have the proof, but I've told you that in infinite dimensional Banach spaces, a Hamel basis is uncountable, while a Schauder basis is always countable. So these two sets will never coincide. And this is a huge difference of these two concepts. Both of them are used to kind of generalize the concept of a basis to infinite dimensional settings. But when it comes to cardinality, they completely differ. What you need depends on what you want to prove. Sometimes it's useful to work with Hamel bases. I usually work with Schauder bases because they're more accessible, let's put it that way. So this is the end of the video. I hope you learned a little bit about the difference of Schauder bases and the Hamel bases. If you have any questions, just feel free to ask me. I will happily answer. And well, take care and see you. Bye.